Perhaps the biggest idea today is this one that's more than 50 years old, from a psychologist called John Carroll, who caused a bit of a revolution at the time, because until then and since, most of the world thinks in terms of students' ability. I cringe when I hear that word, but it is remarkably common, and there's certainly something there. Students have abilities, different abilities. However, if that's how we think of things, it tends to result in limits. You say a student just can't do that well because they're not high ability. Carroll had a different idea, which was to turn the quantity into something that you could control. And he called it aptitude, and he defined it like this. So a student's aptitude for a particular subject, let's say, is how much time they will need to learn something, let's say a particular concept, to a particular level, given optimal conditions. So it's how much time it takes and not their ability. So what's different about students, he said, is that some of them are like hares. They learn fast. Of course, we know that that is partly because they have high cognitive ability, and some students learn slower. They might be more like tortoises. But the analogy is a good one, because if you give the tortoise longer, they can get a long way. And this idea seems very simple, but it's quite profound. What Carroll did was he used this concept to define how much learning a student would gain in any particular case in school. So the degree of learning that student gains is a function of the time they've actually spent engaged in learning divided by how much time they need. Now, it sounds so obvious in a way, because if you spend longer, you're going to learn more. And if you don't spend as much time as you need, then you won't learn as much as you could. But let's go a bit deeper. This time spent in 1963 was as far as he could go. Since then, 20 years later, the world had done loads of research on primary schools and found that what really mattered was not how much time there was in the school day, but how much time students were actually engaged, thinking, academically engaged, and on the critical content that they needed to learn, and were getting a fair degree of success, i.e. not floundering. So that's the time spent. And it turns out that academic learning really highly correlated with achievement. So that this is a real phenomenon. The time needed is what he called aptitude, how long it takes any particular student. And that depends on, obviously, ability, but it also depends critically on whether they're ready, whether they have the prerequisites in place so they can actually get this new learning. And of course, it determined by the quality of the teaching. So once you put those factors in, you start to realize actually the degree of learning is something that we can manipulate and we can maximize. It doesn't have to be some fixed quantity that's beyond our control, that depends on student ability, whatever that is. There is lots of evidence that if you give students the time and the appropriate learning they need, they can be more like the hares and get to where you want them to be. We've discussed academic learning time, ALT as it's called, and the thing that you probably are getting told about all the time is direct instruction. So this might help you if you're a slightly, how should we say, cautious about it, and your school's saying it is sent from God on tablets of stone. This is the way to teach. It all comes out of research in elementary classrooms on learning literacy and maths, and how to maximize that academic learning time. Observing teacher behaviors that increase that engaged time and increased achievement. And all direct instruction is a set of behaviors that correlate with increasing the amount of engaged time. So really what matters is how much time students are spending being engaged, right? So your teaching, whatever that happens to be, is all directed towards maximizing the time spent productively. But it'll never be good enough if it's less than the time the student needs. And that's why mastery learning comes in, because Benjamin Bloom took this model, John Carroll, and said, we can make this work. There's a practical system. It's since been investigated, and obviously lots of evidence for it, but it's not easy to do. There are other lines of evidence. Time to learn, for instance. If you give two groups of students, higher IQ, lower IQ, assessments, obviously, if you have a fixed time, the higher IQ students do well. But if you give the students long enough, that influence of IQ almost goes away. So another line of evidence that time matters. And of course, we know practice is part of the secret. If students get enough practice, repetition, help, support, strategies to do better, then they can overcome what you might call limits of IQ. So very practically, this is what happens in a typical classroom. You've got 3 students, you've got 90 minutes of learning time for this idea in your curriculum. So on the left is a student whose aptitude is 60 minutes. That's how long they need. And you gave them 90 minutes, they're bored. The student in the middle, it's perfect. That's the middle of your class. You've given them the right amount of time. But look on the student on the right, they actually need 150 minutes for a variety of reasons, and they don't get it. So they're going to be stuck. So this is really the conundrum. Fixed learning time means inevitably some students are not going to get up to the degree of learning you want. Why does that matter, right? Because you could say, as many people do, well, it's a spiral curriculum, they'll get another chance later, we'll repeat this, it doesn't matter. Unfortunately, it does. And this is the memory research that shows why learning to the level of mastery or a high degree is worth it. So the top graph shows a kind of learning S-curve with time. So your learning increases gently at the beginning and then more steeply and gets to the top. That's the original learning. And then you finish the topic and you come back to it a lot later. And during that process, of course, we forget. Very well-known fact. And then the second stage, the second peak, is when you try and relearn it, when you revisit it again later. And this is where the mastery learning comes into play. If you got to a high level of learning originally, look what happens. You get the forgetting, but the time to relearn means that you get back to a high level pretty quickly. Compare that with the bottom graph. If students only learned to a smaller level in the first time, then the forgetting happens and they really don't know very much by the time you get to the second stage of relearning. So you never really get them very high on the second stage, and then basically you get either one or two things. You get a continual cycle of having to keep reminding them and reteaching them, or if you did the mastery learning, their knowledge consolidates and builds each time you revisit. And you can imagine the difference in the student's attitude when they kind of feel they know in the top case compared to the fact that they keep forgetting and never really learn it. So essentially, mastery is buying you a shorter time to relearn the same material later. And that matters. The implications for the curriculum. We've come up with 10 of them, and this is really what we've injected into Blueprint. And we're going to go through them with the help of my colleagues now, quite briefly, but some of the materials you'll get after this webinar will go into a bit more detail. So we've broken them into goals, teaching, and assessment. I'm going to rip through the goals section, and then Gemma will talk about the teaching, and Gary, the assessment. At this stage, though, do we have any desperate questions to stop? Gemma.
We've got one, that graph you just showed, what is the time frame of the x-axis on that mastery?
Okay, well, it could be a year. It's not intended to be accurate, but the memory research shows that the time to relearn something is very much dependent on the level of initial learning. So you can forget the graphs being kind of accurate, but that's the key finding of the memory research. So if you want to make something easier to relearn, you learn it better the first time. In other words, mastery provides some kind of antidote to forgetting. So I don't know if the graphs really do show the whole picture, but that's what the research said. Okay, so this is Blueprint in very quick form. The first principle here is we really need to get to the critical content that students have to understand. We're not doing them a good service if we just cover everything in superficial amounts, because that is where we've been, and that's why many students do succeed, because they can figure out all the connections, and many don't because they haven't done that. We're actually going to help them by breaking it down to the essentials. So from 14 big ideas to about 100 key concepts, and for each one, we've worked out, relatively the difficulty and created a progression so that you can keep revisiting the ideas every year if possible, and each builds on the last one. And within the planners, in the new form you'll see, what we've done is we've broken them down further, the ideas. So this is cell structure. Right at the top is the key understanding. In fact, there are two. One of them is life functions, as you can see here, and the other one is building blocks, that cells are the smallest building blocks that are alive in an organism. So these red circled main ideas are the things that students really need to understand, because that's what they use to explain new situations and apply their knowledge. The research is quite clear that that's the sort of knowledge that students most need. They obviously need facts and details and descriptions and stuff, but without these explanatory ideas, you can't explain science. So we prioritized those. The second helpful principle when you're creating a curriculum that's going to get students up to the high level of learning is to help them with the scientific reasoning. In our CPD sessions, we show that questions that apply or analyze can never be done only with content. They assume a degree of inquiry understanding as well. So we have put that into every single goal, and although it's hard, the recommendation is that you're always teaching scientific reasoning as well as content. Come to that in the teaching section. And so here's the kind of objectives that you'll see. So there's critiquing claims, using models. These are the things that students, if they learn them early and often, are likely to be able to use. And they're integrated because we've mapped them from GCSE and Key Stage 3 and put them in every single topic and lesson. The other principle for making the right goals is to make explicit the cognitive thinking that you want students to do. It's kind of there in a paragraph in the trilogy specification, but the rest of the syllabus is all content. And if you only teach the content, of course, you're sort of making a self-fulfilling prophecy. In other words, students who can apply will, students who can't figure it out won't, and exactly what we don't want. So we are going to have, for every single key concept, an acquire objective, like these ones, and then we will have an apply objective, which will say exactly what the kind of task we want students to be able to do with that knowledge. So the first part is how they could learn it, and then the italicized part is how you might assess it. You'll see this when you download the planner. And it has changed. So we've been more explicit about how to use it for teaching and for assessment. So this is analysed. This is equivalent to AO3. Again, if you put these things in black and white, then you can teach towards them and students are more likely to be able to do them. Okay, so that's the goal section. I'm going to stop there. Again, if there are any questions, we can briefly come to them, and then I'll hand to Gemma.
No questions. So
Okay.
I'm going to look at the teaching. So I'm going to show you some of the teaching materials that we've designed, and might give you some ideas about how you can design your own materials based on Blueprint as well. So this is a teaching sequence. These are the different parts of the sequence, and we've estimated time for each part, which will help with your planning. So if we look at the first stage, we call activate. And Tony's already touched on this, but students build new knowledge on their existing knowledge. So before you start teaching them new concepts, you really need to activate what they already know. So we design activate tasks to identify what they know, see what gaps they might have in their knowledge or any misconceptions they might have, which would stop them building on those ideas and learning the new knowledge that you're going to teach them. So this one is designed for the start of cell structure, the key concept. They don't do a lot about cells at Key Stage 2 at all, but they do learn about what's living or non-living, which is important when you start thinking about living organisms being made up of cells. So this task is designed to show what they already know about what is living and what is non-living. And after this, after they've done the task, we expect students to be able to peer or self-assess what they've done. If they've done well on the task, they can go on to a challenge activity. If they haven't, then they do a rethink activity, which will help them make adjustments, make sure they're on track, their understanding is good enough to continue to the next stage. So an example of the kind of the rethink activities you can do, you can go through the information with them as a class or as small groups to check their existing ideas and really question them and get them thinking about what they think and why. So an example of common misconception in this topic is that plants can't move, therefore they're not alive. So you can really question them to think about, can plants move? You know, give them images of plants growing towards the light, get them thinking about, well, actually plants are alive because they can do these life processes. So Tony's already touched on this. So this is part of the planner for cell structure. We split it up into 2 different understandings. Each one of those is worth around 1 lesson. And each one is a suggested acquire activity, which enables students to make sense of the understanding. And in italics, there's a way of assessing it as well. And there's obviously a lot of knowledge here that students need to learn, but there's not enough time to learn everything in detail. So you need to prioritise, and this is how the planner is set out. So the explanatory ideas are the theoretical ideas, and they're top priority because without those, students won't be able to move on if they don't understand those. So you need plenty of time to do those. So that's what we build our acquire activities around, those statements. Also, we have some descriptive ideas and skills, which are also built into the acquire, but they will take less time. And then the details are very, very quick facts and terms that can be just shown on a slide very quickly, not very detailed knowledge. So we really want to get away from students seeing science as just a list of facts to be learnt. We want them to start thinking like real scientists. So we like to base all our acquire activities in real world situations, which not only get them engaged, but also start them thinking about how real scientists like to answer questions and discover phenomenon. And there's 4 ways that you can use to engage students. And we're going to have a quick look at the first 2. I think Tony's going to show you a video of one of them, which is a real phenomenon. We could load up the video. So we used something called a Gauss gun to teach energy transfer.
The Gaussian gun, which I came across from 10 years ago, initially it reminded me of a nuisance cradle with ball bearings, which are going to move. But this is something quite different. There's, in fact, 2 very strong magnets here, neodymium iron boron ones. And when this descends very slowly down the slope, what will happen? Something quite extraordinary. Here we go. Gracious me, it fires like a bullet. How extraordinary. This time we'll try with just the 3 remaining ball bearings. And again, the little trigger one is going to slow, ever so slowly, it'll flow down the slope. Still an astonishing reaction, and notice how far this one came back as well. What's happening here, of course, is that the magnet is attracting this ball bearing at the very end when it's getting close enough, and in the last few millimetres it reaches
back to the PowerPoint. So obviously the Gauss gun is all to do with energy and energy transfers. Yep. Oh. Okay, so this is what you would show the students at the start of the lesson. You would do the demonstration, and there's the engaged question. Why does the outball move so fast? And what they will do is they will do some acquire activities to gain that knowledge, and in order to answer that question, they will return to it at the end, being able to answer it. So they go from not having a clue about what's happening to actually being able to answer what's happening in that phenomenon. Now, sometimes there's no obvious phenomenon that we can use in that way, but there's loads of exciting questions that scientists around the world are actually trying to answer. So we often base our activities on these kinds of questions, crafting them into a realistic scenario. So this is the one for cell structure, so the planner that I showed you earlier, and it's for the building blocks understanding. So students will be told that there's this water collected from deep under the Antarctic ice. It's got these structures, which you can see here. Could they be living? And what they will do in the lesson is collect evidence by using microscopes to look at living organisms and then see if those structures that they see are similar to these ones from under the ice. And this one also is building the reasoning of using evidence to test a claim as well. So they're building in that skill as well as learning about cells being building blocks of life. So the next stage then, when they've done the acquire and they've acquired that new knowledge, the next stage, which is really important, is apply. And that's where we check that they can use that new knowledge in different situations. So this is like AO2, part of GCSE. Now, obviously, this is something that students find really difficult, this kind of problem-solving questions. So we've come up with some strategies to help them. And one thing we've done is we've broken up the process of problem-solving into these 3 stages: detect, recall, and solve. And also we use a worked example. So you as a teacher can go through an example and explain how to answer the question, and then they have a go at their own questions. So if we just quickly look at the 3 stages, so here's an example of an apply question. This is a physics question about calculating weight. So the first stage is called detect, and all that's doing is asking the student, what actually is the question asking you to do? So that's the first stage they need to be able to do. And the second stage then is they need to start recalling all of the information that they know, that they've learnt in the acquire, that could help them answer that question. And you can see it's split up into 4 pieces of information here. So we're introducing one at a time, splitting that up. One of the pieces of information is the formula that they would have learnt in that acquire. And then when they've got that information, then they can go on to solve the problem. So this is the solve stage. This example, a physics question, is to do with a problem and then a solution. So it's all talking about using a calculation to solve the question. So we're categorizing the types of problems as well. A lot of questions are long answer questions, and they're more claim evidence reasoning questions. So that's another scaffold that we would use to help them structure their answer. And as you know, a lot of students have difficulty with those long answer questions. So if we're teaching them another strategy to help them answer those kinds of questions as well. So then, as I said, they will get their own questions to answer. The first question should always be very similar to the worked example, so they can use the same steps and they're going to be successful in answering that. And then the other questions can gradually get more difficult and further away from the worked example until they are getting really good at answering that kind of apply question. Okay, that's it from me. Have we got any questions?
I don't see any burning questions, so let's see how Gary sound. Are you there, Gary?
Yes, can you hear me?
Great.
Is that a lot better than before?
Yeah, much better, Gary.
Okay, thanks. So I'm going to take you through the assessment section. If students are achieving the goals and the stuff that we want them to learn, and we've got evidence through assessing that I've ever done.
Yeah, go slowly, I think. You're breaking up.
And go slow.
Well.
Let's go back. So a lot of the assessments that I've carried out in the past, a lot of them test just the AO1, the knowledge stuff, as opposed to testing the higher level skills, the AO2 and the AO3. And a lot of assessments which we do in schools are normally at the end of topics, end of a whole series of information that we've taught to pupils. And so what we've done with Master It is we've made sure that assessment is carried out throughout the learning process. But also with testing, we also want to give them opportunity to relearn material if they've not fully understood it. So on this slide, which you can see, we're looking specifically at how pupils understood, have they acquired the knowledge about and application for cell structure. So the main focus, which I'm just going to look at in this next example, is for the explanatory idea of life functions. Move to the next one. So this is an example. Go back. So this is an example of a particular test which we did, which was assessing the height. I'll try and go slower. Can you hear me now? Is that better?
Yeah.
So this particular assessment is based on life function, and you can see the questions at the top for acquire and what they're about, and also the ones for apply. And you can see where each of the questions assesses that particular life function. Below at the bottom, you can see we've got a section about misconceptions. So we've tried to build in the assessments, common misconceptions which pupils often struggle with. And you can see there with the crosses where those misconceptions are brought into each individual question. So I'm just going to give you an example. So this is one of the tests, the diagnostic test questions. Now they're all multiple choice questions, which means that you can do a quick assessment and pupils can self and peer assessment really quickly. And you've got that evidence and that data. What you can see from this question, question number one, two of the answers are going to be misconceptions. So over time, if you keep assessing the same sort of idea over time, pupils can't just guess the answer. Eventually, you'll be able to look at the test, analyse the data, and determine if they've not fully understood that idea and if they're holding a misconception or not. So we call these distractors. Evidence also suggests that 3 questions or 3 possible answers is good enough to be able to tell whether people understands it or not. What we've also done for each of the tests or the assessments is we've created feedback sheets. So once pupils have taken the multiple choice quiz, after they've learned some knowledge, and you can give them this grid, and for each of the questions, what the correct answer is. So for each of the questions, it gives you what the correct answer should be, and it also tells the pupils why the other 2 answers are incorrect. So it gives them time to think about why they got that question. So the next slide here looks at, once you have done the diagnostic quiz, after you've taught the acquire and apply information, what we normally say with Mastery Science, people should be getting around 80% of the questions correct. If they've not mastered it and they've not got around 80% on the test, what you can do then as a teacher is you need to give pupils time to rethink and relearn the information that they didn't get correct first time. So what you can do is, after the test, you can give pupils a rethink activity, which I'll show you in a second as an example. And what we've also produced is another diagnostic quiz, which is very similar to the first one, which will then assess them again to see if they've, after the relearning, they've understood the concepts. For pupils in your class that haven't quite mastered the information, then who have mastered the information, you would then give them an analyse task or a more challenging task for them to do. So within that lesson, you might have 10 pupils who have not mastered it, and you're working with them doing a rethink activity. And for the rest, they will be doing the higher level AO3 sort of information or activity, and to push them further, to challenge them further. So this is just an example of a rethink activity. I know Tony and Gemma are developing, looking to develop more of these, which we can use within the curriculum. But this is just an example which we came up with. But at the moment, it will be up to the teacher to decide what kind of activity to do to make pupils rethink about what they've learnt and relearning some of that information from the stuff they got wrong on the assessment test. And then finally, there's the example of a challenge activity for pupils that have mastered the content on the screen there as an analyse. This is just one assessment. At the end of the topic, or end of the analyse and end of the topic, there'll be another assessment which is more formal and looks at AO1, AO2 and AO3 all together. So you can see, once they've relearnt the stuff, do they understand the whole topic as a whole in formative. And this is just an example of the analysis task which can be shown. And that's it from me.
Thank you very much, Gary. So what you've just seen is, just to review, is how we would use an assessment before the end of the teaching unit to see whether students have had enough time. Right at the beginning, we discussed the importance of making time a variable, because students' aptitude means they take different amount of time to learn. And this system is really taking advantage of that concept and saying, have they had enough time? If not, we're going to give them some appropriate activity and an extra learning opportunity to give them the chance to get to the high degree of learning we want, and at the same time challenge other students so they're not just being held back. And that is really the crux of mastery. It's going to require some flexible time, and we've spent a lot of time ourselves trying to make sure that the total amount of content that's in the blueprint scheme is viable. In other words, you can teach it within a year. So that's enough of the theory. We're really pleased to be able to have someone who's doing this in school. And so I'm going to hand over to William to tell you about your work.
Okay, thank you, Tony. Yeah, so I'm from a school in Nottinghamshire called Tuxford Academy. We're an outstanding school, and we've been kind of moving towards a mastery whole school skills-based approach for a couple of years now. And when we sort of analyse our results, our AO1, recall, those sorts of things have always been good. We've got good kids, they work hard, those bits were always fine. But we've noticed that we've had drops in AO2 and AO3, and they're always significantly below. So throughout the school, our assessment system was seen to be too vague, and we were sort of pigeonholing kids, and we wanted to move towards this mastery-based system. So I started looking around and found mastery science that would help us to sort of shift that in science itself. So the first bit that we had to do was make our own progress ladder. So just using Bloom's, we split up our skills. So we did concepts, planning, conducting, and concluding and evaluating. And what we do is we use those ladders in combination with the mastery science content and some of the topic planners to go through and teach. So what we started was we looked at the 5-year plan, the original one, and we've sort of gone along and as things have changed, we've chopped and changed things as well, and we've edited a few things in terms of where we put things, but pretty much keeping to the 5-year plan, making sure that the least difficult concepts are taught first. We then use the topic planners that are provided by Mastery of Science to split each of the topics into distinct levels of learning to match our skill level ladder so that we can assess them. You can see that, I think it's not very clear, but on the bottom right. So we made our own ladders based on those things so that we can see the pathway of the students, but focusing on the fact that we're focusing on the skills, and obviously those skills move through each of the topics. Then when we started to look at sort of how many we've got to teach and those sorts of things, we gave each topic a number of lessons. And then we didn't want this to be a big task for the teachers in the school. We wanted to use old things we've got before and edit them. But obviously what we realised straight away, especially when we started looking in the long-term plan into year 7, 8, 9, 10, 11, is just the sheer extra number of lessons that we've got, because we're not repeating those topics again. We're not going back. We've got a chance to do them more in depth, and we're finding that that's a much better way of teaching it. So first of all, we needed a way of checking previous learning. One of the worries from a lot of the teachers was that there was no way that we were going to know that students remembered things before. So we have used diagnostic quizzes. We've made our own. We've used bits and pieces from Mastery Science to make our own. But every start of every topic and within topics, we use the little quizzes to check that the content is there before we start teaching. So this is a focus that we're moving into year 9, because we're into our second year of doing this. We're in year 8 at the minute. We still wanted to keep the focus of knowledge-based learning. At Tuxford, we do recall tests. So we give them out at the start of the topic. And that's just your core basic knowledge. What does the cytoplasm do? What does the nucleus do? Those sorts of questions. And we test that core knowledge as well. We don't want to lose that focus, but we still want to make sure that in lesson, actually, the majority of our learning is exploring and understanding and giving students their learning in context. We've made our own tests, mainly because we wanted to gear our students towards GCSE style questions, but the majority of those questions are application style questions that we've pulled out. We drop a few content questions in there, and we level those and we grade those and we check that they're fine, but we try and as much as possible to use the application in there. And obviously that assessment needed to fit our new progress ladders. So what we actually did is, one of my colleagues, Michelle, she's brilliant at Excel, so she's made these QLAs, which I'm sure you'll be familiar with. And what we do is we put our marks into those, and it gives us, it feeds all those QLA sheets into a main spreadsheet. So you can sort of see one here. I know it's not the best, but what you can see on the left-hand side, you've got the 5 strands. Those are state, describe, explain, apply, and explore. And those questions, just the ones in lesson, but also the test at the end, it gives us an average of what percentage each of those students are getting in each of those strands. So we can clearly see that, well, what it should be is that the majority of students are pretty much green in those first skills, but actually the harder skills is where students are dropping off, and it gives us a real accurate representation, not just what do you know in that topic, but how well are you doing throughout your skills. So you can see that the other side of that is the year 8 overall averages. And as we do tests this year and as we put more data in, we'll be able to see, obviously what we're hoping is that students, their skills in those areas are getting better as we go through. So what it looks like in terms of actually teaching it, we've gained on average about 5 lessons per topic in year 7 and 8. In comparison to how many lessons we had per topic in the caboodle scheme of work. Now we're looking at that will rise in year 9. We only have 4 lessons a week with our year 7s and our year 8s, but in year 9 we'll have 3. We'll have 2 per topic, so actually 6 in total. So that'll just get more and more and more. So what that means is we're doing loads more practicals, loads more skill-based learning, which obviously the students love and I enjoy more, and I find that students learn a lot better with that. And we also get more time allocated to exploring the application of knowledge. So at the end of each topic, we do a project or we do something where it's a bit more exploring all the knowledge that they've learned, and we just get more time. There's just simply more time to do that. So obviously, as we look forward to year 9, there's going to be even more available time towards that. And one of the things is actually what we've been talking about today is what we want to now filter in is actually, well, we've got the content that they've learned in year 7 and 8. Let's check that they understand that before we move on. Let's make sure that that's secure. And if we do need to reteach that, we do need to re-explore that, we've got plenty of time in year 9 to do that. So it's not that we're just forgetting that we've done this stuff in year 8, 7 and 8, but we're returning to it, checking it, making sure that there's still no misconceptions, and we get more time to do that. Like I said, so we get more time of that teaching backwards. A guy called Mark Burns written a brilliant book about that, and we use a lot of his concepts in terms of pre-assessment and the pathways and things like that, and that's what we base a lot of it on, using the 5-year plan. So what we've managed to achieve is we've made our skills-based progression ladders, so students now know where they're going, we know where they should be going, and we're not just focusing on content, we're actually focusing on, is that student able to stay in each of the topics? Can they state things? Can they describe things? Can they explain things? Can they apply things? And tracking those. And obviously assessment that's linked to that. We're getting more time to engage with science, applying that to real life. Students, I feel like, are being challenged more. I'll explain in a second an example of that. But I find that we're challenging students. It's conceptual change in terms of throughout the years, but in those lessons, we're challenging those students, and it's not just content, we're challenging those students and making them think, making them ask questions. I really love our tracking system. I think it's brilliant. I think we can really monitor the skills as we go through, and actually, because the big part of the QLAs actually themselves, and this forms part of the what we've been talking about as well today, is at the end of each topic, the QLA spits out tasks and things for the students to do to improve on the skills that they've not done well in. So actually, that's actually reduced teachers' marking as well. So we've managed to add more assessment in and have more things in lesson, but actually we feel like teachers are actually doing less. There's actually less for them to do, which is obviously great. So in terms of what we think it is for the students, we can clearly see that working scientifically skills have got better. I was having a conversation the other day with one of my colleagues saying that we look at the year 8s now and we compare them to our year 8s last year, and those students are much better at following methods because we're spending more time doing that. We're not rushing practicals anymore. It was only last week that I spent 3 lessons on a practical. We did it once. I did a demonstration of it. We wrote a method. We spent more time on those skills, which are obviously is into our AO2 and AO3 categories. One of our strands is curiosity in science, and we track character progression through the school. And we're finding that students are much more inquisitive. They're more likely to ask questions because they are understanding these things in a much more depth, and they want to understand things. And we can see the engagement for that just purely because we're spending more time on these. The other one there, Year 7's depth of knowledge is at or above Year 9 students. I teach, obviously, because we've now sort of got two groups now, we've got Year 7 and 8 which are mastery, but we've still got 9, 10 and 11 which are on the old style Key Stage 4 science. And I've done a very similar test with my Year 9s in terms of energy, and just done it with my Year 7s. And actually, the understanding that the Year 7s have got is at or above those Year 9 students. Now, those Year 9 students have seen energy twice. They've learned it in Year 8 and they've now learned it in Year 9. But my Year 7s that have done it once, who are pretty much at the same, I would say, probably the same ability level, we're actually seeing that their understanding, their depth of knowledge is much better. So to conclude, really, it was difficult at first, trying to get my head around how to assess these skills and how to make sure that the skills we were assessing them appropriately, and to get our head around actually only teaching something once before you get to Year 11, but you're revisiting it, you're looking at it again, you're looking at it in a different way, you're applying it in a different way, and you've just got more time. We're finding that students are enjoying science more, we're getting better engagement, and we just feel like the depth of knowledge is improving. And obviously, as we go through Year 9, Year 10, we're hoping that we keep seeing that those skills on the spreadsheet, they keep getting higher, and students' skills keep getting better, and their working scientifically skills keep getting better. Thank you.
Thank you very much, William. I have to say, Will contacted me a couple of weeks ago saying he wanted to tell me how things were working with Blueprint. So he's definitely taken this all by themselves, really, to Oxford Academy, after a session we probably did about 2 or 3 years ago.
Yeah, I think it was about that, yeah.
Yeah. So it can be done in many ways, I think you can see. But at the core, I think what Will's shown us is that if you focus on things that we know are right about science teaching, like going for understanding, teaching in depth, teaching the skills, helping students to go beyond the content and applying their knowledge, then it can work. And what we're trying to do to help that, which has always been true, is that Blueprint is going to set out a way for that to happen, and not to worry about thinking, well, I'm not covering that content, or there's too much, I can't teach this way, I can only afford to do it superficially. And as we've shown, that is no longer the case. There is a way through it all that you can do it. You can get the advantage of learning from mastery, and that means you don't have to continually reteach things from scratch. And that means that you can escape this catch-22 of having to rush through things, so you can have to repeat them again later. So that's great. We're going to wrap it up now, but if you want to ask Will some questions, do chat. If anyone, great. And maybe if anybody wants to contact Will offline, he might be willing to answer your other burning questions.
Yeah, I'll put my email into the chat so people can email me on that.
Fantastic. So after this webinar, you'll be sent in the next couple of days a message which will have the download link, so you can get the latest versions of the planner. Although it's still in a state of flux, we haven't finished Year 9, 10, and 11. And you can get a free topic if you'd like to see how it works in more detail. Take advantage if you want to get a practice book, and certainly contact me if you've got any questions. After that, we'll all sign off, and hope you have a good half term.
Right. So, I'll answer some questions on here. Just looking through. So, someone asked me, how does the QLA spit out tests? We just use mail merge as a mail merge thing that we use with the QLA, so it just will spit out the numbers. If anyone would like an example of the QLA, I can send one out to you. If you just send me an email, I can send you an example out of that. Someone asked about Scheme. It's in-house. We used to use Caboodle, so a lot of the stuff that a lot of the practicals we use and a lot of the textbooks we use, we still use some of the Caboodle stuff, but it is arranged into our own schemes of work. With GCSE, we've written our own schemes of work anyway, so we just pull stuff from there. And that's kind of where we go from. And we kind of take responsibility for one topic each per year. And that's how we split it up, one scheme of work per year.
So how about we just stay online for a chat if people are still asking questions, and we'll go off air otherwise. All right, thanks very much again for coming along.